13.3 electrolysis. So we've just finished voltaic cells, which have a voltage of positive, they're all spontaneous, and it's about making a battery. So it better be spontaneous, because when I plug that battery in, I want the thing to work. Okay, so it better happen without any effort. Put the battery in, it works. So we were making a battery. This is not about making a battery, no. This is about using a battery to force an electron transfer so that you get products you want. In the last one, we got the product because it was the strongest reducing agent, the strongest oxidation, and just gave us products. Okay? So if copper was a product, that's the product. But what if I don't want copper to be the product? What if I want silver to be the product, so I can make silver? I don't want silver to be the loser and copper to end up being made. I want it to go the other way. Does that make sense? Did you notice that we never made silver metal? Okay? We always made the other thing if we had a silver and silver solution. So what if I want to make silver? What if I want a silver-plated trophy, a silver-plated spoon? Okay? Then I have to force the electrons to go the other way, and so that it doesn't go by the strongest reducing agent, but rather it goes by what I want to gain electrons. So electrolysis is used a lot in the industry to get what we want, to get a chrome-plated bumper, to get a silver-plated spoon, to get a gold-plated trophy, to get a etc. Okay, this is, or even to make the sodium that I can then buy to do demonstrations with. Remember that piece of sodium I chucked in the water, it went around, melted into a sphere, surface level, right? Sodium wouldn't have won. Na plus wouldn't have won. It wouldn't have been your strongest reducing or oxidizing or anything. What if I want it to be, so I can make some sodium and then sell it to chemists? Okay, so we do a lot of electrolysis in real life. We do a lot of voltaic cells in real life too. They're all batteries, all the batteries we have. But this is all about sort of what we use in the industry. Okay? So electrolysis, and keeping in mind, you're going to get that definition a little bit confused with this whole unit is called electrochemistry, because it's all about electricity. Okay? And electrolysis is what you do to an electrolytic cell versus the voltaic cell that we've just talked about. So you tend to get all those definitions mixed up because they all start with electro. And then you don't pay attention to the end, and because you haven't paid attention to the end, just pop it all right there, and then you can grab a seat, Lindsay. Just put it, just leave it down. Just put it down, yeah. Okay, so you get them all mixed up because you don't pay attention to the end of the word. It's the end of the word that tells you what we're talking about. Okay, so electrolysis, providing electricity to force a non-spontaneous redox reaction to occur. Electrolytic cell, then, you still have 2 electrodes. You also only have 1 electrolyte. So we don't have to split these up like we had to split up the other ones. And most definitely a power source. So as soon as you see in the diagram that there's a power source, you know it's an electrolytic cell and not the voltaic cells we've just done. Everybody get that? As soon as you see a battery, as soon as you see a power source, you know we're talking about this second half of the chapter, not the first half of the chapter. Okay? On all of the ones that you did, there wasn't a power source at the top. There's a voltmeter, maybe, but not a power source. Everybody okay with that? Okay. So, just as a water pump pumps water uphill, a power source, like a battery pack, can pump electrons against the spontaneity. So it goes against what's spontaneous. An electrolytic cell is the reverse of a voltaic cell. The reactants giving you products and energy is a voltaic cell. If I go, let's see if I can make my pen work today. If I go this way, I'm talking about voltaic cell. I produce energy. If I'm going this way, I'm talking about electrolytic cell. I have to put energy into it. The energy coming from the battery. And here I'm talking about electrical energy. The last unit, this is quite similar to last unit where I was talking about heat energy, right? That I could go both ways on For example, photosynthesis, cellular respiration. One was exothermic, one was endothermic, right? This is very similar, only I'm not talking about heat energy, delta H. I'm now talking about voltaic energy, electrical energy. So, for example, here's a silver ion, so silver nitrate solution, and a copper electrode. This would have been your strongest gaining electrons, reduction, oxidizing agent. This would have been your strongest losing electrons, reducing agent, and always metals are reducing agents. Okay, that's a really good sort of, you know how I keep telling you you should memorize all these shortcuts because they make it faster for you? A really good shortcut. Metals are always reducing agents. Right, the bottom right-hand corner, those are all metals. Those are all strongest reducing agents. So this is reducing agent if you've just sort of gone metals reducing agents. Metal ions are oxidizing agents. Okay, so if this was the voltaic cell that we did in the last chapter, this would have been the strongest oxidizing agent and the strongest reducing agent. You would have produced copper ions and silver. Really? Must be. I must have looked it up on the data booklet when I was doing this. And you would have got a voltage of 0.46 volts. If I want it to go the other way, if I want copper to be made, sorry, I made a mistake at the beginning of the introduction, then I must have mixed that up in my head. If I want copper to be made, I'd have to add 0.46 volts from a battery. Force those electrons to go up the waterfall and produce the other things. Does that make sense? Okay. A secondary cell makes use of this principle. So remember how I've got you to do some notes in your textbook about primary cells, secondary cells. Okay, so a secondary cell makes use of this principle, that we can go both ways on this reaction. So if this is my battery, a nickel cadmium cell, or if I were to have a silver copper cell, this would be I plug in my battery. I plug in my battery and I use it up. The battery goes dead, and I recharge the battery by plugging in, those rechargeable batteries that you put in, right? Or you're using up your cell phone, then you plug in your cell phone and it recharges the battery. And then you use up that battery again, and then you recharge it and you use it, right? So this is a reversible reaction. It can go both ways. So electrons go down the waterfall, then you pump them back up when you plug your cell phone in. Electrons go down the waterfall, you pump them back up. Okay? All right, so this is the summary we need to memorize or understand even better. That the change in voltage at standard, or the change in electrical potential energy at standard, temperature, pressure, etc. By the way, in your data booklet, on these, when we look up all these half reactions, at the very bottom of that page, it gives you the standard conditions. It tells you 1 mole per liter. It tells you 25 degrees Celsius. You don't have to memorize it. You just have to know where to find it. Okay? And you need to know to look for it too. Because the question isn't that, they'll never say a question like, what is the standard concentration for? No. It would say, this cell is at standard conditions. What conditions would need, or here's a student set this up. What conditions didn't they use? And it'll say like it was a 3 mole per liter solution. And so you'll need to know what the difference was. It should have been a 1 mole per liter solution. Does that make sense? So they're never as obvious as to say define standard conditions, because you can just look it up. But they will say what's wrong with this experiment. And you'll be like, oh, it's not at standard conditions. It should be 1 mole per liter. It should be 25 degrees Celsius. Okay? So that you can still get the data though for those questions at the bottom of that. Okay, so voltaic cells have a positive voltage, right? All the voltages we've done so far have been positive. And all of a sudden in these electrolytic cells, your voltage will be negative. Why? because you have to put that energy into it in order for it to work. Voltage is given off in a voltaic cell, whereas an electrolytic cell, it's a voltage deficit, meaning I need to supply it. In the voltaic cells that we've just done, it's positive energy, energy taken in, so this one's going to be energy taken out, needs to be added to react, the voltage does. These are the exact opposite in this manner. There are a lot of ways that they're the same still. Okay, all right, so let's have a look at this picture. It's in your textbook, but I photocopied it for you too so that you could kind of draw all over it. And I've even scanned it to be in color for us here. Okay, so you have a black and white photocopy of this, but here's a scan of it. So this is the voltaic cell that we've just finished doing. This is the electrolytic cell that I want you to now learn. Okay, how do I tell in a test at first glance which half of this chapter I'm talking about? The power source. So here's this battery, there's that power source. That tells me right away it must be electrolytic. Okay? No battery must tell me it's spontaneous. And then just a reminder, although this is the quiz you just wrote, so it should be okay. The electrons are going in this direction. Everybody okay with that? Shows you there, the electrons have gone from the anode to the cathode. The anode is still losing electrons because of that. And so therefore the thing that must be losing electrons must be the zinc is giving up those electrons to become zinc 2 plus. And over here, my cathode is gain of electrons, reduction cathode, and it is gaining electrons, so therefore it's not my copper, but rather my copper ion. So the Cu2 plus will be gaining 2 electrons to become Cu. Cations are going to the cathode, anions are going to the anode. By the way, did we have to look any of that up on the data booklet? No. Did we have to look up our strongest and look up our... No. We can figure it out. That's important for 2 reasons. 1, speed. Secondly, they very well could give you X metal and X2 plus solution. And you need to then sort it out yourself. Okay? Because you should be able to. Over here then, the electrolyte is the exact opposite in terms of the direction I am pumping the electrons. So the electrons naturally flowed this way because the zinc metal and the copper 2 plus were spontaneous. If you looked it up in your data booklet, you would find the copper 2 plus up there and the zinc metal down there. So your strongest reducing agent is below your strongest oxidizing agent. Well, this time in my electrolytic cell, I'm now going to take the zinc 2 plus ions, go up the hill, and make it react with that copper. Okay? So I'm making the zinc 2 plus and the copper react. So I will be forming zinc and forming copper 2 plus instead of reacting it. So you can see the electrons are being pumped the other way. Everybody see that? Direction is different. However, and I've now labeled, the copper is now labeled the anode. Because electrons flow from the anode to cathode. Here they flowed from the anode to the cathode, and here they flowed from the anode to the cathode. So I have to label this stick my anode now, because that's where the electrons are coming out. Yes?
I thought that with the electrolytic cell, it goes both ways, right? Because it goes in one way first, and then you recharge it.
No. So it's going it's going this way when I'm using it in my cell phone.
Okay.
And it goes this way when I plug my cell phone in.
Okay. Okay.
Because here's the plugging in bit.
Okay.
Okay. So not at the same time.
Yeah. Okay.
Right? Yeah. Otherwise, yeah. Let's just leave that. Not at the same time. Okay. Anode to cathode.
So would you label it like
Sorry?
would you label the anode wheels?
Yes. The anode is still Leoa. The cathode is still Gurk. Okay? And what is losing electrons over there? What must be losing electrons? Copper. So the copper, oops, must be losing electrons to become copper 2+. Isn't that what we said was going to happen? Didn't we say over here the copper would be making copper 2+. Okay? And if Gurk is happening at the cathode, well, what is there to gain electrons? Zinc 2+. So the zinc 2+ must be gaining 2 electrons to become zinc. And that's what we said would happen. We said that we want to force the zinc 2+ to be going that way to make zinc solid. And we are. Okay? So it's opposite in what the products get. It's opposite in which the direction of the electrons are flowing. The cathode and anode are labeled opposite, but Leoa, Gurk, still the same. Direction of the electrons, still the same. Okay? So in my voltaic cell,
Junior class change.
which electrode would have been gaining mass and which electrode would have been losing mass? The copper is gaining because I'm making more copper, right? So this would be gaining mass and the zinc would be losing mass. You okay with that? And so eventually in your battery, you would have lost all the mass of the zinc. And then your battery can't run anymore. So then you plug it in. And what are you making over here? More zinc. So you're reforming this stick. And what are you using up here? The copper, the extra copper that you've produced, you're now using that up. Okay? Any questions on that before I go to the next? Okay, so the next bit then, back to the sheet. The next bit I have here is a little table for you, which says exactly what we just said. Okay? So where's Leoa, where are the flow of electrons, when you're comparing the voltaic to the electrolytic cell. I'm going to give you like 6 minutes and 32 seconds to answer that table, and then I'll give you the answers. Okay? Roger, you all right?
Yeah.
Okay. Okay. For Emily's sake, I hope that's still recording. Okay. That's just. Okay, so the voltaic cell should have been hopefully okay for you, that this is still loss of electrons, which is oxidation at the anode, Leoa, right? At the cathode, I still have Gurk. The charge of the anode is negative. Why? Because it's where the anions go. And the charge of the cathode is positive because it's where the cations go. The direction of electron flow went from the anode to the cathode. The direction of the anion flow went to the anode, and the cations went to the cathode. Was it spontaneous or non-spontaneous? Spontaneous. Sign of the voltage? Positive. And does it supply or require energy? Everybody okay with that? Any questions on that? Okay, so in an electrolytic cell, it's still Lioa and it's still Gurk. Okay? The charge of the anode and cathode are different though. The anode is positive, the cathode is negative. Why? Because the cations still go to the cathode and the anions still go to the anode. And because this is coming out of the battery, okay, because it's coming out of the battery, the anode is positive because the anions are attracted to it. And that's what forces it, that's what forces the waterfall to go uphill. Because all of a sudden you've put a battery in it, and the battery states this is negative. Because here are the electrons pumping. So this has to be negative. And the anions go, or pardon me, if it's negative, we're talking about the cathode now. So if it's the negative, then the cations go, ooh, I'm attracted there. And so they force themselves to go in that direction. Because the attraction is greater to that newly found electrode than it was to the spontaneous reaction.
So the cations are attracted to it then, not the anions?
No, the anode is at positive because it's coming out of the battery, because the battery says so.
Oh, so it switches the signs, but you just don't switch the name of it.
Right. You switch the signs, just not the name.
So when, in that booklet that we just saw, it did switch the name though. Like in the booklet, they switched it.
Yeah.
Like that's
Sorry,
what's
I
confusing.
misunderstood what name you were talking about. I thought you meant the name of the anode
Yeah.
and cathode. You do switch which chemical belongs to the anode, yes. Okay. Okay. It is far more helpful if you don't think about switching. Okay? You don't think about how would I change this voltaic cell to an electrolytic cell. Stop thinking about it that way. Start thinking it like this. If I see a voltaic cell, how am I going to label the anode? How am I going to label the cathode? Just like we did for a voltaic cell. Okay, so before I gave you a voltaic cell drawing, and I said go, right? Tell me the half reactions, tell me the direction of the electrodes, or electrons, tell me the name of the electrodes, tell me the, right? I'll do the same thing. I'll say, here's an electrolytic cell, go. Label the cathode, label the anode, which is positive, which is the direction of the cations, which is, okay? I won't say, here's a voltaic cell, switch it all around and make it electrolytic. I won't say that. Because that's, you know, like, what are you talking about? There's too many, like, ambiguous questions that go with that. I could say, here's an electrolytic cell. The student thinks this is, the anode is negative. Is the student right or wrong, and why? And you would say, no, if it's an electrolytic cell, the anode is positive because that's part of the battery, because it's, I might say that. That'd be the closest I'd get to comparing them. Okay, so just looking at the electrolytic cell, which you know because it's got a big battery on top, you would label the anode positive. You would label the cathode negative. Why is the cathode negative? Because the battery says so, right? Remember, you put this battery up. The battery has a positive end and a negative end. So when you put that with wires, that's a negative end. That's a positive end. The end. Right? Your little cell, your little solutions, your little thing isn't going to change what the battery says. So if it's negative, that post is cathode because the battery says. Okay, and because it's negative, that means the cations are attracted to it. And if the cations are attracted to it, then they're able to gain electrons. So we're still talking about Gurk. If the cations are attracted to it, they can gain electrons there, and it's still Gurk. Why are they gaining electrons? Because the battery's firing electrons down that post. Yes?
So it's It's not because, like, once it is the electrons flow to the cathode as a voltaic cell, then it just naturally would become the anode because then it's, because they're pumped over there, and then once it's all done, like, being
Yeah.
pumped over there, then it naturally would switch because now they're all over on the other side.
I guess so, yeah.
Okay.
So when you've got your solution and you've got your U tube and you don't have a battery, there are things in there that want to gain and lose electrons. Why? Because they're more stable. Welcome to science 10. Right? Why does chlorine atom gain an electron so it can have a full valence shell, etc.? Okay, so things want to be more stable. And some want to gain electrons really badly, and some are okay with losing electrons, and you get the stronger reducing agent, stronger oxidizing agent, right? If they're all in there, the strongest and the strongest are going to do it. They're going to switch their electrons. Okay? As soon as I put a battery in, though, now they're like, whoa, some new power has come upon us. And I'm not just going to spontaneously do this little weak voltaic set. That post is negative. I'm attracted to that negative post no matter what. No matter who else is in that beaker wanting to gain and lose electrons with me, this post is far more attractive. Forcing it to do what you want it to do. Okay? The electron flow is still anode to cathode. It's non-spontaneous. Sign of voltage and supply are required. Okay, so highlight on the chart things that are different. Well, this is the same, this is the same. Oops, that's not what I really wanted to do. Same. Charge of the anode, though, is different. Charge of the cathode is different. Electron flow is the same. Anion flow is the same. Cation flow is the same. Spontaneous or non-spontaneous, different. Okay, and if you can sort out the differences and the similarities, then it's easier to memorize. Not because I would ask you to switch the cell, but simply because I think it's easier to memorize if you know the difference. Okay, so on the bottom of this page, I have practice problems for you to have a go at. And the practice problem question 5 is about voltaic cell. And then 6 is electrolytic cell. So I'm asking you to do this chart for an example. Okay, so have a go at that. And then we hopefully have some kind of foundation. And tomorrow, all we're doing is examples. And examples and practice. Wednesday, we write our chapter test on voltaic and electrolytic cells. Great? And then Thursday, we get to look at our tests and make our corrections, Abigail. And then Monday is the unit exam on midterm, on everything we've done. Happy chappies and chappettes? Okay.
Go to the wash.
Yes, ma'am.